Alright, the first part of this video is going to be a little bit of a review, but then we'll have some new information at the end, where we deal with metals where we don't know ahead of time what their charge is going to be. Alright, so we know from previous videos that when we write the formula for an ionic compound, it should have no total charge. And so we have to choose the numbers of the cations and the anions so that the overall ionic compound will be neutral. So if I was going to write the ionic compound formed between sodium ions and sulfur or sulfide ions, because sodium just has a +1 charge and sulfide has a -2 charge, I need 2 sodium ions for every 1 sulfide. So the formula would have to be Na2S. Okay, I introduced a trick in one of the previous videos for determining the formula of these ionic compounds when we know their charges, and I introduced it kind of informally, so I wanted to introduce it a little bit more formally here because I find students often like to use this. So if I wanted to write the formula for the ionic compound made from strontium ions and nitrogen or nitride ions, I would first write down the metal, and in this case the nonmetal, with their charges. So strontium is an alkaline earth metal, so it's in the second column, so it has a +2 charge. Nitrogen is in one column left of oxygen, so nitrogen needs to move over 3 places to get to the noble gases, so nitrogen has a -3 charge. And so the way the swapping works is the superscript, or the charge on one ion, becomes the subscript on the other one, and vice versa. And so we end up with Sr3N2 as our formula. And if we check that, right, 3 strontiums times its +2 charge is going to give us a +6 from all the strontium ions together. For the nitrogen, we have 2 in our formula. Each of those nitrogens is -3, so that gives us a -6. And so the +6 from the 3 strontiums will cancel out the -6 from the 2 nitrogens, and confirms that that's our correct formula. Now there is one drawback to this particular method for writing the formulas of ionic compounds, and I picked this example to specifically illustrate that and make you aware of what you can do to correct it. So if we do the same thing, I want to write the formula for the ionic compound made from barium ions and sulfur or sulfide ions. So barium, also an alkaline earth metal, has a +2 charge. Sulfur is in the same column as oxygen, so it has a -2 charge. So if we swap these, right, we would have said, okay, it's Ba2S2. But when we write the formula for an ionic compound, it's always an empirical formula, because we don't actually have molecules in ionic compounds. So the formula should represent the smallest whole number ratio of the atoms. And because both the 2 and the barium and the 2 and the sulfur are the same thing, so they're both divisible by 2, I can simplify that. So if I divide them both by 2, I would get Bas as the correct formula. And so that's what we would want our answer to be. If you said Ba2S2, that would be wrong. Alright, just a couple more examples of the same thing, only now involving polyatomic ions. So if I wanted the ionic compound formed between beryllium and acetate ions, I would look and find beryllium on the periodic table. It's in column 2. The acetate polyatomic ion is C2H3O2-. So if I swap those guys, I would get 1 beryllium. And then because I have 2 acetates, I have to put the polyatomic ion in parentheses, and then the 2 acetates on the outside. Alright, if we do the same thing for calcium and dichromate ions, calcium would be 2+. Dichromate is Cr2O7 2-. So if I do the swapping again, 2 calciums. Now for 2 dichromates, I put the whole dichromate ion in parentheses, and again I can simplify that. So calcium dichromate should just be that. Now I guess one caveat that I should mention, let's say we wanted to write the formula that was formed between sodium and oxalate. right? I would need 2 sodiums and 1 oxalate. And so we would say that. Now, even though those are all divisible by 2, I can't reduce the polyatomic ion itself, right? So oxalate is C2O4 2-. So I can't make these smaller. I can't change the polyatomic ion. So this one I would actually not reduce because I don't have 2 oxalates. I have only 1 oxalate. And so I would leave that formula alone. Okay, now on to something new. So far all the examples we've done like this have involved metals where we have predictable charges. And so those are the alkali metals. We know when they're ions, they're always +1. The alk and earth metals, when they're ions, are always +2. And then I've also given you that we always know aluminum is +3, zinc is always +2, and silver is +1. But there are a lot of other metals besides these in the periodic table. And so the problem with pretty much all other metals is that they have multiple possible charges. And so if you just told me that we have an iron ion, for example, I don't know what the charge is. And so we have to specify it when we give the names of these. And so we do that with Roman numerals. And so if I told you that you had iron 3 chloride, I'm telling you that with the Roman numeral, what that Roman numeral tells you is it tells you the charge on the iron. So that means that we have, and chloride is the ion for chlorine. And so then the formula for that ionic compound would be FeCl3. Okay, this is just to remind you one more time of the metals that we know and the metals that we don't. Right, so of course the dividing line between metals and nonmetals starts here at boron. Let me go red. Right, so we know that these guys are all +1. Black and earth metals are all +2. We know aluminum is +3. We know zinc is +2. We know silver is +1. So any other metals, all of the transition metals except for zinc and silver, all of these main group metals except for aluminum, all the lanthanides and actinides, they can have multiple possible charges, or sometimes we call these oxidation states. They have multiple possible oxidation states. And so when you give the name, you have to specify what the charge is by putting Roman numerals, or when someone gives you the name, they have to specify what the charge is by giving Roman numerals. All right, so just a couple final examples. If we wanted to write the formulas for the following ionic compounds, right, in each case you can see they're telling me the charge. They're telling me it's iron +3, it's lead +2, and it's nickel +4. So iron 3 and sulfur. Right, when I swap the charges, I get Fe2S3. 3 is not divisible by 2, so that can't be simplified. That's my final answer. Lead 2 and the nitrate ion. So lead is Pb. They told me it's 2+. The nitrate ion is one of our polyatomic ions. It's NO3-. So I need 1 lead. I need 2 polyatomic ions, so I put the polyatomic ion in parentheses. 1 lead can't be simplified, so PbNO32 is our final answer. And then finally, I have nickel 4 and oxygen. So nickel +4, oxygen, ions are -2. So when I do the swapping, I would say, okay, it's Ni2O4. But of course, both of those subscripts are divisible by 2, so I can simplify it. So it should be NiO2.